In Plait, we can write the polymorphic identity function without a big lambda. We just write ident as a lambda that takes x and returns x. And we can apply ident without explicitly picking a type to use for that polymorphic call. We just apply ident to a function, and Plait figures out that ident is instantiated at num arrow num in this case. Now the meaning when we write in Plait is just the same as in curly when we write the big lambda and the @ sign. It's just that Plait infers where the big lambda and where the @ sign goes. In fact, because Plait can always infer this, it doesn't even give us a way to write big lambda or the @ signs. Let's look at how it figures this out. It's got to figure out where to put @ signs and where to put big lambdas. And the @ sign part is easier. Suppose we do write the big lambda, but we don't write the @ sign. So if we do write the big lambda, then the type checker sees something with a for all type, and then it sees a function call with ident here, which doesn't have a function type, it has a for all type. So anytime something with a for all type gets used as an expression, the type checker would know that it needs to get instantiated, that an @ sign needs to go right there. And furthermore, the way it can do that is it can make up a type variable. It can take this type identifier, quote A, replace it with the type variable t1, and it has a t1 arrow t1 that becomes the type of this expression. And then unification and further inference unifies that t1 with num arrow num, and so that's how the type checker figures out that an @f num arrow num should go right here. Figuring out where to put the big lambdas is a little less obvious. So in this case, how would the type checker figure out that it should put a big lambda? And you should have some intuition that the reason is when it does type inference on this right-hand side here, it makes up a type variable for that question mark, and the type variable ends up being unconstrained. We end up with t1 arrow t1. And so when that happens, the type checkers can do the substitution in reverse. It can turn that type variable t1 into a type identifier, quote A, and put a for all around things. So that's how it gets for all A arrow A. And then ident is used, and then it can figure out where to put the @ sign there. So that works out, but there are some constraints on when this can work correctly. Consider this expression, which we've seen before. It's a function that takes an x and then applies x to itself. And when we first started looking at inference, we noticed that this was going to run into trouble. If we say that x has type t, and then we pass it an argument x, that means t also has to be the argument to the function. So we had t equals t arrow something, and then we could keep expanding the t and it would go on forever. So there was no type that we could write here in that type system, and no type we could infer. With polymorphic types, it turns out there is something you could write in place of the question mark, and it would have type, as long as you're also inferring the @ signs, the type applications. And the way you can make it work is by saying that x has type for all A arrow A. And then we instantiate the two x's at different types. So the second x we instantiate at the type num. That means this x has type num arrow num. And so we want to send num arrow num in as an argument to this x, so that one we instantiate at type num arrow num. And it works out. So it's kind of neat that we can infer a type now for an expression that we couldn't infer a type from before. But it turns out we took something that was impossible to infer before and turned it into something that's impossible to decidably infer. It turns out you can't find when for all types let you solve a problem, there's no decidable algorithm that will figure out the for all types and the type applications to make it all work. So to avoid that problem, most systems don't do that. Instead, they constrain the places where they will infer polymorphic types. And the main choice is to constrain it to when you have let bindings. Right? So here I have a let bound ident, and a polymorphic type will be inferred for ident. But in this other example that we saw, where x is an argument, because it's not let bound here, it's just an argument to a lambda, then we will not infer a polymorphic type for this x. Now, we usually say that let is just sugar for lambda. That's no longer the case, as so often happens when we introduce types. Things that could be sugar become more core forms. That's the case for let, when we rely on let to be the point of inferring polymorphism. Right? But this is a convenient and good way to infer polymorphism, because normally you're letting some functions and data types that you want to be polymorphic, and then using them in the body of the let. Or, of course, generalized to definitions in the top-level module in the case of Plait. So this is called let-based polymorphism, and it's a typical way of introducing inference of polymorphism into a language. When you take polymorphism and let type extended with polymorphism, and add type inference, and add inference of polymorphism and type application, then you get a practical programming system. And if we put all of that in curly, we would basically have Plait as well.